Good morning, good afternoon, good evening, everybody. It's Wednesday, so it's EMinar Day, and it gives me absolutely great pleasure to have Andreas Junge talking today on anisotropy. But before I give you an overview of Andreas, I'll just quickly tell you about what's coming up for the next few weeks. Next week we have Jim McNay on airborne systems, unmanned airborne systems, and then following that, Juan Carlos Afonso on his probabilistic inversion. And really everyone should make sure they watch that, because it's a brilliant method where you go from chemistry to physics. And Alessandro Santillano will talk about another probabilistic method, swarm intelligence. And then Phil Wanamaker talking about the real Earth, so to speak, on petrology. Kate Selway and Sinan Ozzadin will tell us about their code, mate, sorry, don't know how to pronounce it, and how they've put laboratory results into their code, and that's freely available. Yasuo Ogawa will tell us about fluids in volcanoes. And then the very last EMinar of the season is Lucy McGregor, who is the SCG's Q1, Q2 distinguished lecturer, who will talk about multiphysics analysis. So today is Andreas Junge, and it really does give me great pleasure to have Andreas speak. I've known Andreas since 1984. We met at an EM workshop in Nigeria, 1984. And yeah, what can I say? I've followed him personally and his career all this time, and he does brilliant stuff. And today, Andreas will talk to us about anisotropy, from basics to 3D modeling. A quick background on Andreas: he did, like many of us in EM, he did physics as his first degree, with a dissertation from Ulrich Schmucker, and then a habilitation from Ulrich as well. Was then taken on in Göttingen as a research assistant, and then followed as a research fellow at my alma mater in Edinburgh. And then since '95, he's been the professor of geophysics, applied geophysics in Frankfurt. And he focuses on geoelectric and magnetotelluric methods, instrument development, field measurements, data modeling, data processing, modeling, and as we'll hear today, anisotropy. So Andreas, I'll stop sharing now and invite you to tell us your story.
Thanks a lot, Alan. Thanks. Yeah, I'm not sure we met in '84 before. At least I saw you.
Yes, we did. 1980, Ife in '84.
Yeah. That's true. Okay. Yeah. Thanks a lot, Alan. Thanks a lot for inviting me to give this talk in this webinar. I think it was great that you and Max, and I think it was you and Max and some others made it possible during these times to come together to give talks. And we just before we were talking about that, this is actually one of the positive things of this COVID situation, that we all have the possibility to listen to each other from our homes and not by spending money for traveling. That's really very good. Okay, so my talk today will be about anisotropy. I'm going to share my screen in a minute. Now everybody should see it. Yes, we do. It's about anisotropy, from basics to 3D modeling. And I say that anisotropy, when did I first start doing something with anisotropy? Well, talking to Ulrich, of course, Ulrich Schmucker, he did a lot, but not so much modeling on anisotropy. We didn't have simply the tools to do this. And I started about 10 years ago with COMSOL Geophysics, and I won't advertise COMSOL, but this is the tool I'm using to do 3D modeling with anisotropy. This software enabled me to do the modelings in 3D, anisotropic, and arbitrary directions. And so I started playing around, and a lot of my PhD students I could convince to do the same. The first one was Michael Häuserer. We tried it out on a project in Uganda, and I'd like to thank all my former actual students to collaborate on this topic. So these are the names of my MT working groups, past members, present members. It was Alexander working in Germany, then Marcel with his Spanish together in the Pyrenees, Lourdes from Granada. She brought data from Tierra del Fuego, I'm going to show in this talk. Philipp Hering, who is still in Frankfurt, who's working on Cembrowski, Mexico. Also had a guest from China, Ying Liu, who brought a data set from Western Junge. Colin Hawk from a data set from the Azores, São Miguel and Sharara Xian and Cesar Castro. They are students right now and ongoing projects in Zagros, Iran and in Mexico. So I'm not going to talk about all these projects, just want to show you where we did some anisotropic work. So the content for today is first motivation. Why anisotropy rather than isotropy? And I'm going to start with the motivation, and after that I'm going to show you some numerical simulations in 3D. As far as I know, not many people have done anisotropic calculations in 3D. Many have done in 1D and in 2D, like the code from Václav in Prague was used many times by many people, but it was 2D, and 3D, this is something really new. And in the end of my talk, I'll give some examples of the real world and indications for anisotropy. So we start with the motivation. Why do I regard anisotropy as important? I start with a numerical simulation. It's a 3D inversion done by ModiM. It was Alexander, my student, who did this. Was published in, well, it's written down in the bottom. And he inverted simulated data. He inverted for full impedance tensor and tipper for 6 periods between 1 and 100 seconds. And it was 20 by 20 sites, so about 441 sites. They were equal distributed 20 by 20 kilometers. And here on the top left, you see the distribution of the sites. And I'm going to show you in a minute. Yep, here we are. So here are the 400 sites, and the results are already plotted at the depth of 5.2 kilometers, plane view, cross-section, y direction, x direction, you see over here. And what is discovered by the data is, well, the conductive body. You have the scale in this area, so conductive, resistive, it's log scale. So we have a body, a sequence of bodies. And in this part over here, you see the fit. So here we have the data of the forward model, and this is the data of the inversion. These are the tippers, visa convention. Periods are over here. And you see the fit is actually not too bad. The fit for sites at, they are here. So one side in the center of the body, and one side to the right and one side to the top right. As you can see, black arrows are real parts, white arrows are imaginary part, and again the fit is pretty good. So one would of course believe the model. Here is the fit for the impedances of diagonal elements, side 2, side 3. Fit is not too bad. Diagonal elements are shown over here. Well, fit could be better. The RMS is not 1, it's 2.89, but still, as you can see from the data, if it was reality, one would say, well, we could live with it. Now, how does the model look like, the true model? The true model, as you probably have expected, it's much simpler. This is the model you would go with if you just do an inversion, isotropic inversion, and this is the original model. It's just one body and two directions. Actually, it's just one direction where the conductivity is different from the background. Background is 100 ohm meter. And this direction is 100 ohm meter, and perpendicular, it's 10 ohm meter. So this is the anomaly. This is an anisotropic resistivity anomaly producing the results. And these results, if you invert them by mod EM, you get the model on the left. So the question is, if we have only the model we get from isotropic inversion, the question is the world isotropic, showing these kind of bodies, or is it anisotropic, showing a much simpler scheme? And if you go a step further, we have a complex structure, high resistivity contrast. The contrast is of the order of 1000 between blue and red. And on the right side, the contrast is just 10, and it's a very simple structure. And if what I have learned when I started with MT, that there's a principle called Occam's principle, if we go for this principle, what model would you prefer? I was told many times anisotropy is much too complicated, but if you look at it closer, you might admit that it's the more simple reality. It's not saying that it is the truth, it's a principle, but it's much simpler than the isotropic world. And this is what my talk will be about today. I'm going to show to you numerical simulations I've done, and we try to understand what's going on physically. As Alan said, I studied physics, so I'm interested in the physics background of anything we see, we observe. Now, the situation is as follows. We have an Earth, which we somehow might model, and it's a 3D Earth, of course. And we assume that we have something inside which is anisotropic. So the rho is a tensor, doesn't consist of just one value. It's more than that because it's directional dependent. And of course, these values depend on the coordinates. And we have observations at the surface at z equals 0. And what we observe are the magnetic fields, electric fields, and we calculate from them transfer functions. And these transfer functions are a function of coordinates, x and y, and period of frequency. In the numerics now, we do modelings in 1D, 2D, and 3D. And what we get, again, is the components, but additionally, we get the EZ component, and we can calculate electric currents. This is all what we can calculate. We don't measure this. We measure the effect of that. And these are complex numbers, so we get a real part, imaginary part. They are functions in space and functions of period. We're going to talk about the dependency of all these fields within the body, within the Earth. And what I said, it's the tensor of the resistivity. It's just shown here, different components. We've got the major axis and we've got also off-diagonal axis. They are, well, stating that the world can be regarded as anisotropic. Now, this is the general scheme, and we start with a very simple 3D model study. We have a body which has 40 kilometers by 20 kilometers and 10 kilometers thick. And it has anomalous resistivity. This is the anomalous resistivity in the background, or normal resistivity is shown here. And what I'm going to show to you is now, at first, an example with an anisotropy, or anisotropic direction, rho 1, 1000 ohm meter, rho 2, 10 ohm meter, and the background is 100 ohm meter. So in one direction, the resistivity is higher, and in the other direction, it's lower than the background. I didn't write X and Y. I read rho 1 and rho 2. These are the principal axes. the principal axis of the anisotropic directions. Now, the examples I'm going to show to you is with a slightly rotated, we say azimuthally rotated principal axis. So rho 1 is rotated by an angle of alpha with regard to respect to the major axis. All right. What are the results? Now, we start with an isotropic body. So such an isotropic body, what you see here is the response, rho A, y-axis, in a plane almost 100 by 100 kilometers. And the colors are log resistivity. So log resistivity of rho A yx for a period of 10 seconds. And here for a period of 1000 seconds. So short periods over here, long periods over there. And what is the difference between top and bottom? Well, we have on top, we have yx, shown here, yx, and here we have xy. So all this is xy, and here we have yx. And we nicely see what everybody expects. We see the responses we see in conductive body. So in the isotropic case, this is very simple. The two polarizations stand, or the two yx and xy stand for different polarizations. And as the x coordinate is in this direction, the magnetic field is polarized in that for rho yx and the electric field perpendicular. And we see very nicely that for that polarization, that part of the body here is referring more to the TE mode and here to the TM mode. And you can nicely see the responses, the different behavior of the responses. And for the bottom, it is vice versa. So in general, in the isotropic world, this is easy, and this would be easy to invert. Now, we show the tippers. Schmucker's tradition, Wiese convention, so Parkinson would be the other way around. Wiese means the induction arrow is pointing away from the conductor. We have two arrows here, a black one, which is the real part, and a gray one, which is the imaginary part. Nicely to see. For 10 seconds, short period, opposite, parallel, but opposite direction. For long periods, parallel in the same direction. So here are the tippers. Of course, the tippers do not refer to a special polarization. Both polarizations are needed to calculate the tipper. All right, so we move on. We'll have a look at the phase. Phase, again, I don't go through all these details now. The scale is shown here. So red is high, blue is low, yellow is 45 degrees. And we see a good conductor. So we have a phase above 45 degrees, which is pronounced for 10 seconds, less pronounced for 1000 seconds. Before I leave, I come to the anisotropic. We have a short look for the resistor, rho A of a resistor. Again, we see the resistive body, both polarizations, nice to see. And we go to the phase. And the resistor, we see a phase is hardly to see. And this is, of course, one of the messages MT is sending, that we see conductors and not resistors. And you see it nicely here in this example. So we come back to the conductor. Come back to the inductor, to the apparent resistivity. This is what I just showed you. And now we come to the anisotropic anomaly. And I've chosen the anisotropy, as I said in the beginning, one direction, 1000 ohmmeter, the other 10 ohmmeter. And this is for an angle alpha equals 0. So rho 1 is pointing into x direction in this slide, and rho 2 in this direction. That means currents which flow into that direction, they see a conductor, and currents which flow into this direction, as in this example, they see a resistor. If we plot the rho A values, we get this pattern up here resembling to a conductor, down here resembling to a resistor, because the anisotropy or the principal directions have the values I'm showing here above, 1000 ohms, 10 ohms. For the tippers, this is now very interesting. The tipper, which is point inside, I just showed here, the same tippers in all plots, of course, because we need both polarizations. So a tipper for a side in this location points inside, and for a side on top, it points away from the conductor. Why is that so? Because the tipper here is referring to electrical currents in that direction, and these currents, they see a resistor. Currents flowing into this direction, they see a conductor. Now, what makes, or what is the reason for induction or a tipper vector? The reason is a boundary, either here or either on that side. And it counts what difference or what gradient of resistivity you have at that boundary and what you have in that boundary. And here again, it is the resistive, conductive against resistive, conductive background, resistive body. And on that boundary, or to use the arrow here, it is the other way around. And that makes the induction arrows look a bit strange, but it's easy to explain. You can imagine this will be a problem if you invert this isotropically, because the isotropic inversion has to use an isotropic model to explain this feature. And of course, this is hard to do. Now we are rotating the anisotropy. Here it was 0 degrees, and now we go to 30 degrees. And what we see is that, for instance, here the arrow, here the arrows, they are giving the direction 30 degrees of the tipper, but it's not always like that. We have arrows pointing in completely different direction depending on the location relative to the body. So it's not straightforward to deduce from these arrows. It's not straightforward something about anisotropy. It's getting even more complicated. And what we saw before, I'm just moving backwards to the 0 degree, we see the anomaly here now clearly, and it is disappearing because it's a mix. It's a mix of both 110 ohm meter and 1000 ohm meter approaching the background of 1 ohm meter. So it is something which is now even harder to detect. Now let's go a step forward. Let's go to 40 degrees, no, 45 degrees, sorry. 45 degrees. Now, for 10 seconds, the anomaly has almost disappeared. We still see the tippers. And it's a complicated pattern showing up for the long periods. So what we learn from now is, from these slides, is that the pattern for a simple, very simple anisotropic body will be not so easy to interpret. Okay, let's have a look at the phase. Now, this was the isotropic case. Isotropic case, phases for both polarizations and 2 different periods. Now have a look at the anisotropic phase. I move towards and backwards. Of course, you see here, it's almost disappearing. There's no phase. Why is there no phase? Because this polarization is referring to the resistive part of the body. And we learned that for the resistor, the phases are not seen so well, or almost very, very small. The difference is to 45 degrees. And that makes it for the phases even more complicated or more difficult to interpret if I have anisotropy. And now I'm rotating as before. I'm rotating to 30 degrees and to 45 degrees. And now for the 10 seconds, we have a mix. We see some phases, but again, the pattern is rather difficult. It's not as clear, not at all as clear as for an isotropic world. Okay, so this was a first impression, how these, a very simple 3D anisotropic body, what this body will cause for our, transfer functions or responses. Now, these are the most simple responses being used for many, many years. There are some other responses, and I'm going to show you these other responses in a minute. So let's recall some of these definitions. We've got the impedance tensor, the apparent resistivity, and then we've got the phase tensor. Phase tensor introduced by Caldwell, Beebe, and Brown, and almost 16 years ago now. And it was a bit, John Booker called it a revolution in MT. It's the phase tensor, I think, known to most of us. And Colin produced 13 years later another paper, and now he made the full tensor, the apparent resistivity tensor. And this is a new quantity which I more and more use because I think that this quantity has some advantages towards even the phase tensor and of course towards the presentation by impedances and apparent resistivity. And I'd like to use the opportunity to introduce this apparent resistivity tensor, which in fact connects the electric field, which quantity Colin calls apparent current density. So it's in a way, it's Ohm's law, but the currents are induced currents by the magnetic field. So it's not geoelectrics, of course, it's MT, but currents are currents, whether induced or not, and they can be conducted to the electric field by Ohm's law. Now, rho is a tensor. It's the apparent resistivity tensor, rho, and we will meet that in a minute. I'm showing you now a graphical presentation, which my student Philip Herring published in JGR recently. And this plot is just to show you how we present the tensors. The tensor ellipses have been introduced for quite a while, and John Booker gave a very nice review on the phase tensor and also different possibilities to display the tensor. Philip has found a nice way of combining the ellipse of a tensor presenting phi max and phi min. And normally the color of the ellipse is used to refer either to phi max or phi min. He has introduced this little bar here, and the color of the bar is the color of phi min. And now by this presentation, we have the values and not just the ratio, the aspect ratio of the principal axis. We have the values of phi min and phi max, and we regard this way of presenting the tensor or the ellipses as advanced because it gives us more information, at least graphical, optical information than before, where you had to deduce from the aspect ratio the value of phi min. And the values are displayed normally as a function of period, which is shown here. And now this only serves to show you the conventional phase tensor, a circle if there's a 1D situation, and if there's 2D or 3D or anisotropic, then it is an ellipse. It turns to be an ellipse. Now, the apparent resistivity tensor offers the possibility to plot either the real part or the imaginary part, and these plots are shown here, or a phase deduced from, as for the phase tensor, from the impedance tensor, deduced from the apparent resistivity tensor. This is the, well, we call it RPT, the resistivity phase tensor, and this is shown here of the apparent resistivity tensor. Now, rho A and phi are almost the same, despite that there's a shift of the from 45 degrees to 0. So where you have 45 degrees for the phase tensor, it's 0 for the apparent resistivity tensor. I'll show you a comparison in a minute, but this is to show you the kind or the way I'm going to display the data. A very simple example to remind you, isotropic world, 1D situation, conductor between 2 and 4 kilometers depth, 1000 ohm meter background, 10 ohm meter the conductor, and this is the typical curve, the rho A curve we have, and the phase curve, which is shown here. Depending on the period, high frequency, short period, long periods over there, and the red line, the blue line is the normal rho A value from the impedance, and the red value is the value from the resistivity tensor. For the phases, conventional phase from impedance, and the phase below in red, it's the phase of the resistivity phase tensor. And you can see it's it's a very similar shape, but it's a little bit more pronounced for these values. Okay, now this is the curve for the isotropic model. This talk is about anisotropy, so I show you immediately the response for the anisotropic part. For the isotropic part, well, anisotropic part is here. Now, what is anisotropic? It's a very, very simple model again. We have background 1000 ohm meter, both here, and also this y direction is also 1000 ohm meter. So if I'd use another pen, this direction is as the background. So the whole anomaly or the anomalous layer is coming from that direction, which is a response, a red arrow. It's this color, it's 10 ohm meters. So we only have a conductive response in that direction. How does it look like for the phase tensor? You all know the phase tensor, short periods here, circles, yellow, which means 45 degrees. And then we have a split. We have a phase above 45 degrees in that direction. And the bar now, very important, the bar is yellow, which shows there is no change with longer periods in the direction of the bar. If we go down here, it is again this direction, which is yellow, and the bar now is grayish, which is below 45 degrees. So the color of the phase tensor is telling you there is something conductive, this boundary here, and again resistive following the scheme, but the other direction stays yellow, so no response, no anomaly in that direction. It's much easier for the apparent phase, the phase of the resistivity tensor. Direction is the same, and yellow means we have a transition into a conductor, and blue means there's a transition from a conductor into a resistor again. And what we also see is that the bar, here you see the bar is always, well, he pointed at gray. Gray is 0 degrees, nothing is happening. Now, one step more, if we go to the real part of the apparent resistivity tensor, the real part of this tensor, it shows you directly what happens as if you had a rho A value, but this rho A value now has directional dependencies. And it shows that the direction in here, shown by the ellipse, is staying blue, which means there's no anomaly in the rho Y direction. And all what you see is the anomaly in this direction. And now the colors, the scale referring to U is here. The colors tell you, there is a conductor, as you would see for rho A values, but now rho A values in this direction. Now, this is the big advantage we have using the values of the apparent resistivity tensor compared to conventional values. so far some definitions, and we go now a step ahead and look what happens inside the body, what happens inside the Earth. On the left side, we have the conventional features. You all know this, the relation between B and E for a 1D subsurface. It's straightforward that the faces are connected by 180 degrees. And we have a relation for B and also for E with depth according to the skin depth. And this is the value at the surface. And at the surface, we form this ratio. But at any part for a homogeneous half space, we have this relation between the magnetic, orthogonal magnetic and electric field. So this is easy to calculate. And we do this now. We see the situation for homogeneous world for 10 ohm meter, homogeneous ground, 10 seconds, 10 ohm meter, 100 seconds. And this is the depth is here. So we see a much larger penetration depth, and if the period, if the subsurface gets more resistive, the penetration depth is of course deeper. And we can show a little video showing blue is the magnetic field, red is the electric field, and we see the magnetic field with depth and with frequency as a time-dependent function, and the electric field is of course 45 degrees phase shift. So we see these behavior for different depths and for different periods. Okay, so let's go to anisotropy. We have a conductivity tensor with conductivities at the principal axis, sigma 1, 2, and 3. These are the three principal axes. And in general, we can rotate into any direction. We can use the Euler transform and Euler angle to rotate such a tensor and rotate it. If you do it, but it's not very general, it's just a rotation around the z-axis in this case. And we have an azimuthal anisotropic situation. And so we can derive the conductivity tensor for any situation. And Ohm's law then is connecting the current densities with the electric field by this tensor now. And because we have to use the tensor to relate the electric field to the current density, it is very obvious that the current density is not parallel anymore to the electric field. For EM, that's rather important because the currents are correlated or related to the magnetic field. And that means this orthogonality relation between electric field and magnetic field is also not valid anymore in an anisotropic world. And this makes things, of course, extremely complicated, especially if it comes to inversion procedures. I'm not going to talk about inversion in this part. We stay simple. We stay simple, but there are two possibilities of describing azimuthal anisotropic conductivity. You can have a conductivity described in the principal axis by the matrix here. And if the sigma ZZ, as I would call it, is equal to this orientation, then we have a kind of dike structure. The anisotropy is described by the whole body. It's a bulk anisotropy. And of course, this is only for demonstration to show what such a tensor will cause for the electric currents. Or we have what I call a kind of pipe situation. There, the resistivity or the conductivity in Y direction is the same as in Z direction. So these are the two different situations. There actually, I found out not very relevant to MT, because we have in general horizontal or very pseudo-horizontal currents. Of course, if there are anomalies, there are vertical components, and this might have a certain effect. I'm going to show to you this later, this effect, but just to keep you in mind that we have this situation here again. In general, for azimuthal anisotropy, we have such a conductivity matrix or tensor, and it depends whether sigma zz is equal to y prime or x prime if we have the left or the right scenario. Okay, how does it look like if we now go to what I just showed to you, the distribution of these fields for the situation 10 ohm meter 100 seconds, but now in direction 1. We have a polarization of the magnetic field, the situation for a polarization, which is shown here. Polarization is in that direction. And if we go on, and oh yeah, and the electric fields are now shown in different depths, 0, 20, 40 kilometers, 60 kilometers. So 60 is about here and 20 is about here. Okay, so these are the situations for a polarization in that direction. If we go on and go to a polarization in this direction, the situation is described on the right side. And here we have now not a conductor, we have a more resistive ground, and this means the fields penetrate into the earth much deeper, but only for this direction, for this polarization. If we have a mix of both polarizations, then again, things come and stay complicated. I have now a magnetic field polarized into that direction at the surface at 0 kilometers. For this instant, it's turning around the magnetic field because we have different penetration depths for rho 1 and rho 2 for these anisotropic directions. And if we now switch on the movie, we have a linear oscillation on the top, but electric and magnetic field are not perpendicular anymore. And becomes worse at depth, we have elliptical polarization due to the different polarization depth or skin depth depending on the direction. Again, this is the reason why inversion makes it so complicated, as if we compare the same period, we are referring to different depth depending on the orientation. And this is something, this is not easy. Now, we have a look. This is all shown in the publication by Philip in JGR, yeah, 2018. And he gives an example for, again, an isotropic situation. Here is the body we just saw. And we see the distribution of the electric field for short periods and for long periods. So short periods finish here, long periods, it's much lower than 10 kilometers depth. And here we see it for the magnetic field. And here we have the electric current, the current density. For short periods, we see nicely that the current density is concentrating at the top of the conductor. But for the long periods, the current density is almost the same in the whole conductor. So different situations. And we have a look now for the anisotropic case for the short periods, which you see in a moment. This is shown here. Again, the anisotropic model we saw before. And one plane shows the orientation of EX, and here in EY. And the anisotropy is only in this layer here. This is anisotropic with a slightly rotated orientation axis. And now we see for the orientation showing the conductor, we see the same situation as up here. But on the other side, because it's slightly rotated, we also see the conductor now for a field which is not aligned to the principal axis of the anisotropy, which is slightly rotated by here minus, I think it's minus 20 degrees. Philip chose, yeah, here alpha minus 20 degrees. So this is what is happening inside the body, and we can also look at the face. On the faces, there's a phase transition, which is, of course, with a penetrating wave at depth. The phase is rotating. If it's approaching a resistor, a conductor, then we have these kind of jumps in the phases. But this is just to show a picture of the phases. Okay, now we go to 3D, to the isotropic world in 3D. And I show you 3 studies. I show you an anisotropic cube within an isotropic half space. I show an isotropic cube above an anisotropic half space, and at the end also dipping anisotropy. Okay, let's start with the anisotropic cube within the isotropic half space. And the cube, you know already, it's the cube I had before, and it's quite clear, the dimensions. And now the anisotropy, to make it a little bit easier, the background is 100 ohm meter, and we have just one conductor in a certain direction, rho 2, and the angle is by alpha or gamma, in this case, 30 degrees rotated. So this is the situation. I show you the case for different angles of rotation. So all what we have is now an anomaly for rho 2. Everything else is background. To make it the most simple case in 3D we can look at. Just one component being different from the rest of the world. Background 100 ohm meter. It's an azimuthal anisotropy. So the rotation of the principal axis, rho 1 and rho 2, is around the z-axis. So this is the rotation. So these are the different situations. Okay, let's have a look how the response look like. Phase tensor. Phase tensor on this side, same plot as previously, not ellipses, crosses to make it a little bit more clearer. We have, the scale is over here, maybe hard to see, 45 degrees, above 45 degrees red, below blue, and we see the conductors for 10 seconds. We see this body very nicely in this area, but just by one component of the phase tensor. And here we have the real part of the resistivity, of the apparent resistivity tensor, of Collins' new resistivity tensor. And also here we see now the impedances, and we see the impedances 100 ohm meter everywhere. Also in this direction, slightly different, but not much. And in this direction, we nicely see now the resistivity or the conductive direction of this 3D body. So we have a nice possibility of showing for such a side distribution, the existence of an anisotropic body. Here is the imaginary part. I don't go into detail for the imaginary, but just want to show you that the distribution shows very obvious that there is a body which is anomalous in the center. Coming back to the plots I showed you before, what we have already learned, these are the rho A values, these are the phase values, and we see in rho A, yx, we see nicely the body, and we also see now the tipper vectors pointing at this direction. Here on that side, we see the phases and indicating a conductive, well, something conductive underground. If we go inside the body and look at the current density, then the current density is high for a certain polarization. I come to that in a moment, within the body, of course, because this direction is conductive. And so we are going to look now what is happening inside the body and producing something we observe at the surface. In this talk, I'd like to show you the reason for what we observe at the surface. So if we go above the body, this conductive body, we also see something. These are the currents, the current direction, and the current direction shows there's also a deviation of the orientation, even if you're not inside the body. And this is something which is obviously a bit strange. So let's have a look in more detail at the situation. Here we have the anomalous body. We have a look at HX polarization. Well, the x-axis is this axis here. And here are the orientations of the anisotropy. So the anomaly is only at rho 2 directions. The angle is 30 degrees of the rotation. The arrows, which you see here, show the current density. And now come to the colors here, red and down, they denote the vertical component of the current. I have somehow to show the vertical component. So there are currents diving into the conductor and coming out again, having a slight current, a slight vertical component. But it's very, very small. The scales are shown on that side. Relative scales for the arrows, and here 0.6 for the colors. So the vertical components are very, very small. Now this is the situation for a plane view through the conductor. Within the conductor we see this, and on that side it's just to show you the phase tensor and tipper, what we see on top, of course, of the whole situation. But the reason why we see that, it's within this plane. It's within the conductor. So now we learn that the tipper arrows result from currents which are oriented in this direction, and therefore the tippers are pointing in that direction. And this is what you see here. So we nicely see now the reason for the rotation of the tipper. Now let's have a look what happens above the conductor. Show you, here is the plane. Now it's above the conductor, and above the conductor we have currents now also slightly being rotated. The question is, why do we have such a rotation? If we move further, if we move now inside the body, it's like that. Oh, sorry. This is now for HY polarization. Before it was HX. For HY polarization, normally HY, this direction, currents orthogonal, this direction. This is what you see outside. And inside, the currents are deflected into that direction because of the conductive area in the direction of rho 2. So this is straightforward that we see this situation inside the body. And also, again, you see that this refers nicely to the direction of the induction arrows. If we move up, again, we have a deflection of the currents, although the plane I'm showing to you is not cutting the conductor, it's above the anomaly. But still, we have a rotation of the currents. And the question is, how can we explain the rotation of these field vectors? Now, I'm going to show you a situation for a very simple two-layer system, isotropic above, anisotropic below. And the orientations of the anisotropy are like that. Just before, we have sigma 1 and sigma 2, showing two different values of sigma. And we are looking now at the behavior of the electric field when diffusing into the subsurface. The basic equation is the Helmholtz equation, and according to this equation, we have an upgoing and a downgoing part, and we are looking at the downgoing part, which is denoted by y. So this is at the top, at the surface, and at the bottom, at this boundary. Now it has decreased, of course, according to this equation, and we have now a smaller xt. When we want to find out what wave or what part of the electric field is reflected, is going upwards, we have to project the field onto the principal axis of the anisotropy. And the principal axis, one axis is this one, and the other axis is that one. So these two values here are that arrow and this arrow. This plus this gives the one which is coming from up, and it's now having this shape at the transition zone. Okay, how do we calculate the upgoing part? We were talking about this part. Now it comes to that part, because we have a reflection at the boundary, and the reflection coefficients is shown here. You can derive that by the continuity equations using the magnetic and the electric field. And then you can calculate that part which is reflected. And now look at the details. This part is this one, and this one is that one. Why are they opposite? Over here, same direction as the yellow arrow. Here, opposite direction. This depends on the conductivity. If the conductivity of the top layer, which is here sigma 0, if sigma 1 is smaller, then this one is negative. If it is larger, it is positive, or vice versa. If it is smaller, positive, larger, it's negative. And so depending on the two conductivities relative to sigma 0, it depends whether the arrow is pointing that direction or that direction. And I've shown you now this example, and this is part of the upgoing wave. Now, what wave's going up? Now, we have to add the two light blue into the dark blue, and we get the dark blue vector. And this one is the vector going upwards. And here it is at the surface again. So at the surface, according to this diffusion equation, or the solution of the diffusion equation. And so at the surface, we have this part of the upcoming wave. And now what we observe, of course, it's the sum of the electric field, which was propagating downwards, and plus the field coming upwards again. So we're observing this electric field. And of course, this is rotated, but if we compare it to what happens at the bottom, we have to add the yellow part here and the dark blue here, and we get this arrow. So rotations all around. And now hopefully you can understand why we have rotated fields in a medium which is not isotropic, but which is above the anisotropic medium. Everything what is reflected by an anisotropic medium automatically gets a rotation, and everything which is in this space here is suffering or is affected by this rotation. And on top of that, in a different way, the rotation angle is not constant. It's different here from there. And you can imagine this makes things not easy again. Okay, now we have a look at what happens above an anisotropic half space if we don't have a homogeneous layer, but if we have an anomaly embedded in this. And everything what you see here is isotropic, but it is above something anisotropic. And we have just learned that everything what is reflected is affected by the anisotropy. So it also is affected, or everything what happens in the anomaly is affected by this anisotropic subsurface. And this is the reason why we see a rotation of these arrows, even if there is no reason for a rotation, because everything what happens here is in an isotropic world. But if we have an anisotropic surface, it makes things appear as if something anisotropic is within this region. And if we go now and have a look what happens inside the this whole volume, and we go to 12 kilometers, which is inside the anisotropic surface, the whole currents, of course, the currents are rotated. This is very normal. But if we now move to a layer which is at 8 kilometer depth, still beneath the anomaly, but within the isotropic body, we see a rotation. And now we have learned this rotation outside of any anomaly is coming from the reflection by the anisotropic surface. And of course, if we move now into the body, which is here, now the plane is within the anomaly. We are looking at a plane in here. There, of course, we see the high current density within the body. And this is very normal. And this is, of course, also causing the appearance of the induction arrows, which we see over here. Okay, here we have now the appearance at the surface. We know now what is happening down there. And now we see what is happening at the surface. I compare now for a period of 10 seconds the phase tensor and the real part of the resistivity, apparent resistivity tensor. For the phases, we hardly see anything. The body is somewhere here. We hardly see anything because the effect of the body is somehow low, but of course we have an aspect ratio in the phase tensors coming from this from the anisotropy. However, the 3D anomaly can nicely be rotated by the real part of Collins' resistivity tensor. It nicely shows that there is something which is less than 100 ohm meter, but in the background, here's the scale, a bit hard to see. Rho A values 30 ohm meters, 120 ohm meters over here. So we nicely see it now in the resistivity tensor. And just to show you the imaginary part of the resistivity tensor, it also shows nicely the appearance of this body, but I don't go into detail now. Okay, the final example, a numerical example, is the dipping anisotropy. Dipping anisotropy means we have now conductive direction 100 ohm meter, like the background 100 ohm meter, and it is conducting in this direction and orthogonal to it. It's but hard to draw. I couldn't succeed so good. So I tried to show you the situation in another plot. This is what we saw before. And now we have a dipping anisotropy. And the very general term, we have now the full matrix. Remind you, the matrix is symmetric. So here it's an axis of symmetry. And so we have a dipping anisotropy now, which, well, there might be cases in reality where we have this case. Here we have the result, dipping anisotropy in this 3D body, and we see the induction arrows, and we see a strange behavior of the rho A values. Just to show you the isotropic cube, this was an isotropic conductor, and here dipping anisotropy. Very, very different behavior of these curves. I don't know what will happen if you try to invert such a vector. I haven't tried up to now, but can do this in the future, of course. Now, the dipping anisotropic cube, dipping anisotropy again, rho L values and phase values. And if we go to the apparent resistivity tensor, we have the phase tensor over here, and we have the apparent resistivity tensor on here. And it's hard, there is an asymmetry. If you compare these two sides, it's more orange here, more greenish here, the bar, but hard to see. Whereas here, the anisotropy is much easier, or the different behavior is much easier to be seen in the apparent resistivity tensor. And if we go to the imaginary part, it's also nicely to be seen. So far the numerical studies, and I'm talking now more than an hour, but I hope it's okay. Some much shorter examples from the real world. I start with case one with the African rift. Why do I start with this one? This is, to my knowledge, the first publication ever done for anisotropy case in 3D. As I told you in the beginning, there were lots of publications. Wiebke Heise, for instance, and Czech colleagues have done a lot about anisotropy, and Anna Marti has given a review on that. And so a lot has been done, but all calculations, forward calculations, were done in 2D or 1D in an anisotropic world, but not in 3D. And the first time which has been done, when this had been done, is by Michael Häuserer, a former PhD student of mine, on a project in the African Rift. This is the only photo, I'm afraid, I show in this talk. And this is Michael setting up one of the geomags in Uganda. It was in Western Uganda. You see the African Rift Valley and the East African Rift. The Western one is here. And this was our target. It's blown up in this area. We have the Rift Valley, it's here. And here is the third highest mountain in Africa, the Rwenzori Mountains. And the question, of course, is why the hell is a mountain within a rift? This was the target, and it was not just MT or many, it was a big project. So we had quite a number of sites at that time. It was much. Nowadays, I would say it's just a few, but never mind. What Michael got is these nice phase tensor crosses, in this case for 156 seconds, and these are for the long periods, and scale shown over here. And I just want to draw to your attention to the model data on the observed data. The model responses match pretty well the observed data. The problem we had, why did we start with anisotropy at all? We didn't see any tippers there. The tippers were extremely small. So we had to model the anisotropy, and we had to model it. And it wasn't enough to have this graben, because the graben was too small. It would produce tippers, but we didn't see any tippers. So the question was, why, how can we get such a modeled data? And what Michael found out was an anisotropic, modeling an anisotropic layer beneath 20 kilometers. Modeling this layer, this could explain the data. So it was all 3D. The situation here is 3D above an anisotropic layer, and one direction is shown here and one direction is shown here. And now the question is, why do we see this resistor here? We must be extremely careful. We don't see the resistor in this polarization because of the conductive orientation, the conductive direction. It prevents the wave polarized in this direction penetrating deep into the ground. So only one polarization is left. And of course, one cannot do much interpretation for the deeper Earth interior. What Michael found out was, this was a bit striking. We had assumed that the conductive region is maybe due to some faulting along the rift, but no, it is perpendicular to that. And he explained that with some orientation, different orientations for olivines, referring to the geodynamic situation. But I don't go into any detail in this talk. I just want to show you some results hinting at anisotropy. Okay, so this was one of the examples. The next example is from Tierra del Fuego. Tierra del Fuego, the data set came from the Spanish colleagues from University of Granada, and Lourdes González, who did her, I supervised her PhD, did a very nice interpretation with our Frankfurt software, also modeling 3D anisotropy. The general situation, you know that South America, Antarctica here, South America here, and these were the area where the measurements had been done, and there was a setup of several sites. You see the area here displayed, and in the next plot we see the results. So we didn't do any inversion, we just did forward modeling. The field data you see here for 100 seconds, 1000 seconds, and 6000 seconds, so long periods. And what we see is phase tensors and in red tipper arrows. Okay, so this is shown on this part here. And Lourdes tried to explain the data by just modeling the bathymetry, by modeling some isotropic asthenosphere, and some models she detected or derived from the sedimentary situation in that area, and then using an anisotropic asthenosphere. And we were surprised that the orientation of the tippers, you see the tippers here, it's coming from the shoreline, but it's not pointing to the shore, as in this situation where we just modeled the bathymetry. It's rotated. And this rotation can only be produced, or we just could produce it, by an anisotropic asthenosphere. The asthenosphere doesn't produce the tipper. The tipper is produced by the shore. But the rotation of the tipper, and this is what we learned previously by our numerical studies, the rotation of the tipper is produced by something anisotropic. And this was the reason why Lourdes set up a forward model with an isotropic continental crust, and she had basins up here and had the ocean and lithosphere and a complex or an anisotropic asthenosphere. And this was then possible to match, we thought, pretty well the data. And the scenario she developed, I'll just show you the scenario, is some anisotropic area related to the geodynamic processes in this area. Okay, and the last example is from Cembrowski. This was a dissertation from Philipp Hering, former PhD student of mine. He did measurements together with Lourdes González in Mexico at the Cembrowski volcano. The situation is here. We have the world and Mexico, and we have within this part of Mexico, we have the Tepic Zacualco rift. There is a line of volcanic areas here, here, and there. And Cembrowski, that's the sea. This is one of the volcanoes. And here you see the setup of the sites in this area. High frequency sites, broadband sites, low frequency sites. And Philip did a ModEM run, inversion run. And these are the models for, well, it's minus 0.5 kilometers because it's related to sea level and it's above sea level. So we have some conductors. Red is conductor, blue resistor. And if we move to downwards, we see the situation here. Now, if we have a cross section at the volcano, we see nicely, well, maybe it's a magma chamber or these typical conductors beneath the volcano. And this is for 10-kilometer depth. And ModEM produced something which gave, now the scale is very different. This is 100 kilometer, and here it is just 12 kilometer. So the area is here, and outside, ModEM produced these anomalies. They were necessary to explain the data because the data had a very small tipper but a large aspect ratio. Now, from the isotropic inversion and the observation, you see the comparison here. We see the ellipsis for the phase tensor, and here the resistivity tensor, and here we see the tippers. And actually, if you compare observations and isotropic inversion, so we compare, for instance, we compare this plot and this plot, it's not too bad. The RMS is plotted here, the NRMS in this part here, and here's the deviation of the phases with period. Here's the period. So actually the fit is not too bad. But if we look closely, the colors up here of the ellipses are a bit more reddish than down there. And the question was, is it possible to explain these ones? And the other thing we didn't like at all is what we see here, these strange conductors, resistors produced by ModEM. And if we move now, we couldn't explain that. And the question was it possible to explain the data not using this part at 10 kilometers and beneath? So Philip derived an anisotropic forward model using the results from MODI-M for the top 10 kilometers. He was using these results, but then he replaced the body by MODI-M by an anisotropic body of 1 ohm meter and 80 ohm meter in that direction, and it was slightly rotated by 20 degrees clockwise. Okay, and now the result, it's plotted up here, and you see it resembles the data much better than the isotropic inversion, and it does not need these conductors and resistors outside. And the RMS, well, the RMS of the isotropic model is shown here. It's the dashed lines. And if you look at the scale, there is a deviation in the phases, which is far from zero, also for the anisotropic model. So it doesn't solve everything, but it does explain the area, we would say, as well, maybe slightly better than the isotropic inversion. And what is very, very important, without the body which was shown before, without the body shown in this area. So we get along with something which is geological, of course, much more realistic. And if we come now, well, come to the end now, how can we deal with existing isotropic 3D models? We have lots of isotropic 3D models which do exist, and my former student Ying from Wuhan University, he has published in JGR a very nice result of his study in China. It was also a nice anisotropic model he developed. And what I show here from his work is a study he did for an isotropic and anisotropic situation for his sites. He had 3 lines above isotropic and anisotropic body. And when you do a MODI-M inversion on this situation above, on this situation, it recovers very nicely. We know MODI-M is fantastic if it comes to isotropic inversion, and we very nicely see this body. But if we have an anisotropic situation, it also retrieves the body, but it produces something outside. This is nothing new. This has already, well, Ying has shown it very nicely here, but it has been shown a long time before by NASA. Some of you listened to his talk 2 weeks ago, and he has done a publication, EPSL, on US array data, he and co-authors. And NASA already mentions in his publication that the situation here gives features which looks like having an anisotropic origin. So it's nothing new what I'm saying, that the world is anisotropic. At least NASA has already discovered this in his data, and you also can see it for a deeper zone, but this zone, it's much nicer. And if we compare these data now to what I showed to you in the beginning, the case study I showed you in the beginning when I started, also inverting something anisotropic. And if you look at these patterns, they very much resemble the patterns you see over here. And so it's really straightforward that in the data NASA is showing that there can be an anisotropic origin. What is a bit striking is that the density of the sites does not produce a higher or smaller layout or sequence of resistive and conductive bodies. It stays like this, but this might be a way of how the inversion is being, or the parameters of the inversion have been chosen. Anyhow, NASA already mentioned in his work, he doesn't show a picture there, a figure there, the publications by Long et al., and it shows that the orientation of the SKA wave splitting, the fast axis, is in this direction here, and it's slightly rotated up there. And this might refer to the two orientations, which are also seen in the MT results Nasser is showing. Okay, so this is the look into the future. I would suggest that compared to these isotropic Dike models, which you could see with, I would say, unrealistic high resistivity contrasts, I would prefer bulk anisotropy, which should yield much more realistic and moderate resistivities. So I come to the conclusions. There are clear indications for anisotropic conductivity. And I'm not the first one discovering this. This has been mentioned also by Alan. I mean, there are many publications in the past mentioning that. The question is magnetotelluric the only method? At least seems to me. What is definitely necessary is an array site distribution. And the preferable observables, to my point of view, are these complex resistivity tensors published by Colin in JGR. And it's one of these papers, no figure at all in one paper, but yeah, it's Colin. And Herring then has together, it's Herring, Colin, and myself who published this paper in JGR showing an application of Colin's complex resistivity tensor, and Tipper, of course. It's always very helpful and necessary. Then the comparison with seismic anisotropy, as many people before myself mentioned, it's really necessary, although the reactions might not be parallel, but the pattern is important, and this might change spatially, of course. And last but not least, of course, directions are always very important and helpful for understanding geodynamic processes. Okay, I stretched the hour. It's now 20 past, but I hope I could interest you. Thank you very much for your attention, and I'm ready to answer questions, if you like.
Absolutely brilliant, Andreas, absolutely brilliant. Really brought home how important this is. Do you mind if I just jump in and show a couple of slides, some overheads?
Yes.
Okay, I've got something that really brings home exactly what you're saying, because some people are wondering. There's a question from Dennis Woods about the applicability, and I'll just very quickly show this. I don't want to steal any of Andreas's thunder, but this is one of the largest known anomalies on the Earth, which is the Paleoproterozoic trans-Hudson origin that welded Eastern and Western North America together, and smack in the middle of it is this great big conductor, the North American Central Plains conductivity anomaly, that was mapped initially in the 60s by Ian Goff, and then we've mapped it continuing all the way through. We actually went and into, most of it is undercover, I should say. Sorry, most of it is undercover. But we went up here and collected rock samples, and you can see positions of rock samples. There's this sample here, LP94-7, by this. There's a lake here called Sulfide Lake, which kind of gives it away. So this is a cartoon image of the rock sample. Sorry, the omega didn't appear here, but you can see that these are 1-inch cubes. You can see at 1-inch cubes, very high anisotropy. Yeah. When we go in and do scanning electron microscope, the grains perpendicular to strike, the pyrite grains are not connected, but along strike they're connected by pyrite stringers and iron oxide. And so here we have at the grain scale anisotropy. Sorry about that. Sorry about that. But
Alan, about what depth do you expect these grains? I mean,
well, I mean, the NACP we see down the crustal extent of it. We see down to 10 kilometers. Yeah. I mean, this is a longer story, and I can map it from the surface to the mid crust.
Yeah, but Alan, you see, you're really touching the point. I mean, the world is anisotropic. Exactly. We're both convinced. Exactly. but
exactly.
deriving the depth, it's pretty complicated.
Yeah.
As I pointed out in my talk, you know, it's really complicated because anything anisotropic will influence everything around. And this is something we have to deal with. But there are challenges for the young ones, Alan.
Yeah. Well, perhaps I'll give a talk on this in the EMinar next series. Anyway, let's get to more interesting things.
Yeah. There are some questions in the chat. So how do you go on? I mean, should I answer the question?
What I'd like to do, if it's okay, I'd like to read out the question so it gets in the recorded version. And then
okay.
So the first question is from Pavel Alexandrov. How is the effective electrical conductivity, sort of micro anisotropic parameters, calculated for the pipe model?
Good question. So the pipe model is just to demonstrate how it works. I used the possibility in COMSOL to model a complete anisotropic conductivity tensor. So I'm giving the values of the tensor elements into my model, and then I calculate, or COMSOL is calculating the fields and the responses. So I'm not using pipes. It's just for demonstration that the directions are different, and we have to distinguish between, do I share the screen? No, the screen is not seen. Can I share the screen? Just a second, I share the screen and I show you. Yep, now you can see it. Just a second. And we are coming to this model here. And it is really only to demonstrate the difference between this and that matrix. Here we have the same conductivity in that direction and this direction. And in this case, we have the same conductivity in this direction and this direction, but not here along the pipes. So by this model, I only try to demonstrate the different matrices producing anisotropy. But in the model, I'm only using values for this one, or as I show, or for here. Okay, so I'm not calculating an effective conductivity.
Yeah, that pipe model is exactly what I saw in those grains in for the Trans-Hudson origin.
Alan, this would mean that you should have the same resistivity in that and that direction. However, in MT, it's irrelevant as long as it is horizontal. If it's dipping, this is something, oh, Alan, we have to talk about this, because if there is if there's some indication for deformation producing a dipping angle, then this should be seen. But okay, this is another topic maybe.
Yeah,
but
I'll send you the data.
Yeah, good. For MT, you see, most of the currents are going into this direction. There is hardly, well, if there's a deviation, it's very, very small. So for the current, it's really, it doesn't matter if it passes here or it passes here. Same situation. It's only different if you looked at currents in this direction. But in MT, we don't look at this. So for MT, this situation is not relevant.
Moving on, Dennis Woods asks an interesting question. What evidence exists that geological conductors typically encountered in mineral exploration have anisotropic conductivities? And that's Dennis's question is the one that prompted me to show those. By direct physical property measurements or rock samples, or by borehole physical property logging. Same question for more general conductivity anomalies in the Earth.
Well, cannot say much to that as I'm not a rock physicist. However, what I would assume is we have the situation you just showed, Alan. However, we might have more macroscopic like fractures and faults, which you can detect by a borehole or by samples. But for the bulk conductivity, you need a statistical distribution or some more information, which has nothing to do, or at least not directly to do with anisotropy. It really depends what I call on the bulk property. And a bulk has a size which is not detectable, not resolvable by MT anymore, which in turn, if you have 1 kilometer depth, these are sizes of 500 meters, which we cannot detect by MT. So everything what has a size or is in this scale will produce something which looks like an anisotropic feature at the surface, but in terms of samples, it can be isotropic samples. So this is a question we simply cannot answer directly from MT. We have to have other information.
Syed Mohammed Abdar Faroushi asks, thanks for your interesting presentation. Is it possible to consider the direction angle of anisotropy being itself an unknown model parameter? Or you always define the anisotropy axis beforehand? Yeah, Syed asked this question before you went on to talk about dipping anisotropy. If the form is the case, yeah. So I guess you answered that later on in the.
Yeah. I think so. Yeah.
So his next question, Syed always likes to enjoy asking lots of questions.
Oh, you can go on, no problem.
How do you satisfy the boundary conditions in the forward modelings when the anisotropy exists, and how you can remove static shift and galvanic distortion? Does it mean that we always have charge accumulation on the boundaries? If yes, how can you force that your forward modeling codes to converge?
Yeah. Well, the answer is very simple. I did finite element modeling, and I had a mesh adapting grid. So I could expand the model to a very large extent, and the boundaries were isotropic. So if there's any region anisotropic, I just made it very large, and the boundaries for my models were isotropic. And charge accumulations at the boundaries, if we have a dipping, it's this very interesting question. If we have a dipping anisotropy, what happens at the surface of the Earth? The currents, they are rotated. And the currents, of course, if the electric field is parallel, tangential to the Earth's surface, and the currents are not parallel to the electric field, what happens? And it's exactly what Syed says, the Earth's surface has to be charged. This is also an interesting question. If anywhere in the world we have such a situation, dipping anisotropy coming, outcropping, then that would be interesting to have an experiment to see if the charges can be somehow observed. Interesting question. Yep.
Yeah, certainly, and also the galvanic distortion one. That,
yeah. Well, galvanic distortion is, of course, I mean, yeah, it's not resolved by anisotropy. It's independent from anisotropy that we have.
Yeah, and the phase tensor is galvanic distortion free, but not Colin Brown's.
Exactly. Yeah.
So Sergio Espinosa, who is also called Mr. Anisotropy.
Okay.
Wunderbar, Vortrag, besten Danke.
Yeah, okay.
The real world, especially the subsurface of the Earth, is indeed anisotropic. Why do you think geophysicists, especially those exploring for minerals, have disregarded and almost denied this important physical principle? You showed convincing forward modeling. When do you think we will have a breakthrough in anisotropic inversions?
Oh, wow. Well, why do you think geophysicists? I think geophysicists have thought about anisotropy, of course, and in the seismic community, they are talking about anisotropy almost for ages. And yes, of course. I mean, it always depends on two major things. One thing is to have the measurement or the instrumental ability to have array observations which are necessary to say anything about anisotropy, and then of course the modeling tools. And it was a very long time we couldn't model anisotropy in 3D. So what did people do? They had these dikes and modeled in 3D isotropic, but using dikes and trying to explain the world. But it was, of course, not easy. And I wouldn't say they have denied it, but yeah, maybe some did because they didn't want to enter this anisotropic field. Inversion, anisotropic inversion. I heard some rumors that some guy in North America is trying to do this anisotropic inversion in 3D. I try to point out that it's not just putting something into a box and trying and getting out some anisotropic model. By trying to tell you what happens inside the Earth, I wanted to explain that the things happening by anisotropy are by far more than just double complicated by having one parameter more or two parameters more. And the big problem I see is that we can have an orientation, which I showed in the example of East Africa, which might be damped because of a good conductor in one direction, in one polarization. And then we see only the orthogonal polarization for greater depth. And then how shall we explain the Earth just having this component? We must have many sites, of course, but we are losing one component. And we also, what we always, or not always do, but what we try to do, we are saying that similar periods refer to similar depth. But this is definitely not the case for anisotropy. So if we want to calculate the Jacobian and we are doing something for a certain depth, we are changing the model parameter, trying to get the response on top for a certain period, then the effect will be very, very different depending on the grade or the amount of anisotropy. So these are all things which make inversion, I would say, extremely complicated.
Yeah, even in an isotropic case, Andreas, you know, you have different periods of sampling different depths.
Yeah. But not as strongly as in anisotropy. Yeah.
Okay, well, the next three are really just comments and okay. Thanking you for wonderful presentation. I'd like to echo that. That was absolutely wonderful. We should let everybody go. Thank you very much again, Andreas, for this absolutely enthralling walkthrough of anisotropy, and it really has opened our eyes.
Thanks a lot, Adam.
Just like to remind everybody, next week's seminar, EMinar, is from Jim McNay, and it will be at midnight UT. That's sort of Thursday morning for those of you in east of Europe, and Wednesday evening for those of you west of Europe. So see everybody next week, and thanks very much again, Andreas. Bye, everybody.
Alan, thanks a lot.
Bye.
Good.